Okay, but those electrons have to have somewhere to go. So the zinc metal forms Zn2+, and then these electrons go through the wire that's connecting it to the other side of the electrochemical cell. And so over here, what's happening is these two electrons have to go somewhere. So the copper ion solidifies because the electrons go into it. So the two electrons, the source of the electrons is, that zinc. And then as soon as it gets into the solution, they hop onto a copper 2+ to make copper solid. So the reaction that's happening on this side is copper 2+, and 2 electrons get added to it to create copper, the element. So if our acronym is Leo says GER, the one that's losing electrons is oxidized. So losing electrons means they're a product. So this side is being oxidized. The side where electrons are gained of electrons is reduction. So this one is reduction. Hence the term redox, right? One side is reduced, that's the copper, and one side is oxidized. That's the zinc. Now, there's one other important thing. We have to have a salt bridge in between each side. This is because if you don't, it short circuits your process here. So you get all the electrons stuck on one side and the charges don't balance out. So instead you got to connect it with this bridge where ions can flow in and out of the solutions without, without creating an imbalance. We wouldn't want all the negative charges on the cathode. That would create a mess. So oxidation is loss of electrons, and oxidation happens at the anode. So another phrase to remember is anode oxidation, anox, and reduction at the cathode, red cat. Anode and cathode. And these names come from a familiar term to us. So what we have here is a place where the negative charge is. So anode is negatively charged because that's where the electrons are coming from. And so anions, right? Anions are negative ions. So anion, anode, very similar. Cathodes are positively charged because cations are positively charged. So there's a lot of memory devices to use here. Red cat tells me that reduction is happening at the cathode, meaning that, electrons are being added to an ion. Okay, so in order for a battery to actually conduct electricity, you need to have a situation where the element, like zinc, is higher up the chain than the ion. So let's take a look. Zinc and copper. So zinc is right here, Zn solid, and copper ion is down here. So this reaction will create a battery. It will do a redox process. If I tried to use the solid copper as my source of electrons and produce and use zinc ion, that would not go. Nothing happens. Okay, so it's like the opposite. So, a little summary. Anodes are where electrons are generated. They are the most active metal. So like zinc was the higher up in the activity series. So that's going to be the anode. And what's actually happening there is that electrons are transferred from the solid to become an aqueous ion. At the cathode, the cations are there. So copper 2+ in the last example, it's a cation and it's hanging out at the cathode waiting for some electrons. The cathode is always the least active metal because it's the ion. Okay. So the question is, when does a battery stop making power? And what can we do about it? Okay. And so when we look at this figure here, this battery, the arrow points in only one direction. So what is actually physically happening over time is this zinc solid is ionizing. It's becoming Zn2+. So eventually we're going to run out of solid zinc. Also, the copper ion is becoming copper solid. So like this chunk of copper, as we go along, is going to be getting bigger and bigger and bigger and bigger, which is great because copper is actually way more expensive than zinc. So the size of the metal over here is physically getting larger as we go along, and the size of this one, of the zinc, is actually, disappearing. So batteries stop working for one of two reasons. Either you have completely run out of zinc, in this case it's zinc, but maybe, you completely run out of the anode, or maybe you have completely run out of the ions at the cathode. Either one of those will cause the battery to die. So something most people don't know is that your water heater in your house actually contains a battery, because there's a lot of ions in water. And so the lining of a hot water heater is made to be a cathode, and then you stick an anode in there so that over time this buildup is minimized, right? So you can add electrons to it and sort of create a place where all the solid, lime builds up, instead of ending up all over the water heater. It just kind of collects in one place, and you can trade that out. So a lot of people's water heaters die when the anode has disintegrated completely, because then you've got all this built up calcium in the water, and that's bad. So, if you're a homeowner, you need to do maintenance on your water heater, or else you're going to be buying a new water heater every 5 years instead of every 15. Anyway, so water heaters have anodes to help prevent scale, we call it, lime buildup inside of the water heater. Batteries kind of work on the same principle. Once the anode is used up, the battery stops working. Once the anode in your water heater is used up, it stops protecting the water heater from hard water. Okay, so the way to fix it would be to add more solid. Like, you can replace the anode. It's just a thing that screws into your water heater. It's usually not that big a deal, although consult a plumber if you've never done it. But you can replace that anode, and it will extend the life of your water heater. Or in a battery, if I replace the anode, suddenly my battery works again. As long as there's still cations at the cathode. Now, this question: does the rate of the reaction depend on temperature? The answer to that is yes, absolutely. So if we think about this, so here's our battery. If we increase the temperature, you get more ions dissolving, which is great because that means the reaction goes faster. So batteries are temperature dependent. If temperature goes up, a battery works better. It discharges better. So you can think about it like more energy. On the other hand, that means your anode gets used up faster. So, in a hot water heater where it's heated, that's an issue, right? It means that you're using up your anode more quickly than you would if the water wasn't hot. But of course, then it wouldn't be doing its job. Now, this has some important implications. I had this car, a Honda Civic. I bought it brand new, but so, I knew there was nothing wrong with it. But every 2 years, like clockwork, on Thanksgiving weekend, the battery would die. And it took me the longest time to figure out why. 4 years of chemistry classes, actually. And what it boils down to is that around Thanksgiving, the temperature outside goes down. And so, as it turns out, my battery was, not very happy in that situation. So one thing you can do if your battery dies is take it out of your car and bring it into the house for a little while where it's a little bit warmer. So by increasing the temperature, you allow the battery to work better. So we have lots of examples of wet batteries in everyday life, one of which is car batteries. There are lots of examples of dry batteries in everyday life too. So, for example, AA's, AAA's, all those Duracell type batteries are dry batteries. And so here's a diagram. If you did cut through a battery, here's what you would see. The anode, which again is where oxidation occurs, anox. The anode is a combination of like a zinc that is the casing of the battery. So like the outside, the very outside is plastic, the label, but underneath that is some zinc solid. So that's your element. That's what the source of electrons is. And then right in contact with the zinc solid is a paste made out of manganese oxide and ammonium chloride. And so this is a base, and it's capable of being ionized. The cathode here is actually kind of like a carbon rod, and the carbon isn't actually conductive. I mean, it's conductive, but it's not actually going to lose electrons. What is losing electrons is this pasty stuff, this yellow stuff in the middle. And so a battery runs out when you've exhausted the paste and or the zinc of the casing. The graphite rod is actually that little bit that sticks up. So cathode is where reduction occurs. And we said it was positively charged. So every battery has like a little metal disc sticking out the top, and that is always marked with a plus sign on the side of the battery. The negative part is actually the casing on the bottom down here. That's where you access it. And so you can plug like a light or whatever, this is a light, into this by connecting it to the positive side and the negative side, or a remote or whatever. And so that's how a battery works. So this is an acid type battery because NH4 is an acid. And they're like the cheapest kind of battery you can get. Duracell makes them, and Energizer, and all of those. They don't last as long as alkaline type batteries, which are usually marketed as like high efficiency and for photography and things like that. These actually do last longer, but they cost a little bit more. They use potassium hydroxide instead of ammonium chloride. So ammonium chloride is cheaper. And so potassium hydroxide is a little bit more money. So they cost a little bit more. But they do last longer because zinc is more stable in a base than it is in an acid. So depending on the application you're using it for, sometimes it's more efficient to get a more expensive battery that actually lasts longer, has more energy in it. Another kind of dry battery you might have seen in a hearing aid or the fob of your car or something like that. They're little button batteries. And these ones operate on a kind of a similar principle where the anode is the zinc, and you got your positive access where the cathode is here on the top. And then on the inside, you have a mercury oxide, KOH, paste. Now, mercury is not so good for the environment, so these batteries should not be disposed of in the trash. They should not go to landfills because mercury can leach into our water, and it's a poison. The regular Duracell batteries can certainly go in the trash. They can also be recycled. The button batteries all have to be recycled. You're supposed to take them to like Utica has a waste handling facility. You can take it there. Sometimes Lowe's and Home Depot accept these things and recycle them for people. But you're not supposed to throw those little flat button batteries in the trash because they contain mercury. They have less energy in them than the acid type and alkaline type Duracell batteries, but they last a longer period of time. So like your car fob doesn't need to continuously transmit electricity, it just needs to do it occasionally with really small amount of energy. So it's a good idea to use those longer lasting batteries, but things like Xbox controllers need lots of energy, so AA batteries it is. Okay, so wet batteries, like in your car battery. The car battery is made from solid lead and solid lead oxide and some sulfuric acid, and it forms lead sulfate and water. These are very toxic. They're very dangerous, so you shouldn't handle batteries on your own. But basically, your battery is pretty cool because it can discharge, meaning it can go the front ways to produce electricity, or it can go backwards because it's in equilibrium. And so that allows the battery to be rechargeable. So car batteries last even longer than button batteries do.